Hello everyone. First of all, allow me to congratulate each one of you for getting selected into the PGP here at Indian School of Business. Hearty congratulations. Through this audio-visual tutorial and another one, we will try to prep you for one of your courses in the very first term of the program, the Statistical Analysis course. In this tutorial, we will learn about the idea of probability and random variables. But before that, we will briefly revise the different types of data. We will also go through the formulae for various measures which are commonly used for summarizing a set of data. Following this, we will acquaint ourselves to the idea of a random variable and probability distribution of a random variable. The key here would be to understand the relation between a dataset and a random variable. We will also look into some methods of summarizing a random variable. We will then move on to some pictorial representations of data. And lastly, we will discuss linear combinations of independent random variables. So first, let us begin by revising different types of data and some summary measures. Shall we? We have all learned that data can be measured on one of the four scales: nominal, ordinal, interval, and ratio. So what does it mean for a particular data set to belong to one of these types? A nominal data depicts categories. For example, the various undergraduate degrees earned by PGP students. A list containing the degrees of each one of you would make a nominal data, wherein there is no measurement or ordering between a BTech degree and a BA degree. An ordinal data moves one step ahead in this direction. It contains logical ordering or ranking of the items. For example, business school rankings. Ordinal data still does not convey any information about the numerical measurements of values. So in the business school rankings example, saying that the difference between the first and the second ranked school is 1 unit, or the difference between the first and the third ranked school is 2 units, has no meaning, right? This ranking could have very well been top, middle, and bottom and would have conveyed the same information. The number assigned here has no significance. Interval scale data takes care of this numerical significance as well. So a statement such as, tomorrow's temperature in Hyderabad will lie between 22 to 25 degrees Celsius has a meaning. However, even in this type of data, saying that 20 degrees Celsius would be twice as hot as 10 degrees Celsius does not have a meaning. In addition to this, a zero in the interval scale is not a true zero. What I mean is, 0 degrees Celsius temperature is not indicative of there being no temperature at all, correct? Lastly, the ratio scale, where ratios are of course meaningful. It is correct to say that the sales of a particular new smartphone doubled in the second month of its launch as compared to the first month. Also, a zero sales here would really mean that no product was sold. Therefore, ratio scale is said to have a true zero defined for it. Now suppose we have a data set in front of us. What can we do with a bunch of numbers? Here are some of the ways in which we can summarize the data and produce meaningful findings. I'm sure that all of you have learnt about these before, and so this will only be a revision for you. The summary measures mentioned in this slide are based on n numbers. Let's call them A1, A2, A3, so on up to AN. The arithmetic mean of a data is calculated as the sum of all numbers or data points divided by the number of values in our data. So here, arithmetic mean is equal to summation of all AIs, where I takes value from 1 to n divided by n. The median is that observation which divides the data into two equal halves. It is that value above and below which 50% of the values in the dataset lie. So the formula for calculating median is looking at the n plus 1 by 2th observation when numbers are arranged in an increasing order. The mode is that value in a dataset which appears the maximum number of times. Or to say, it is that value which has highest frequency. So the first three measures were measures of central tendency. They indicated typical value in a dataset. Some more examples of measures of central tendency can be quartiles, geometric mean, etc. Now, what if we want to get an idea about the variability existing in the data? Here, variance is the most commonly used measure of variability. Broadly, variance gives us an idea about how far the data is spread out from the arithmetic mean. Variance is calculated as the average or mean of squared distances of observations from the arithmetic mean. So for our set of n numbers, variance can be calculated as summation of ai minus arithmetic mean the whole square summed over all values of I going from 1 to n divided by n. Now since we square the distances, the unit of variance is not the same as the units of measurement for the observations in our data. So another useful measure for variability can be to calculate a standard deviation, which is nothing but the square root of variance. Let us now understand the concept of a random variable and study the idea of probability distributions. In the last two slides, our discussion was based on just a set of numbers, any set. But often in real life, the dataset may have been generated by a specific process or would belong to a known phenomenon. For example, we may have demand data for a retail store, or we may have observations from a laboratory experiment. Can this make our lives easier in some way? If we know that the set of numbers at our hand has been generated by a single process, is it possible that we can handle the data more effectively? A random variable describes the probabilities for an uncertain future numerical outcome of a random process. So what does this mean? Simply put, a random variable is a variable because it can potentially take one value from the set of many possible numerical outcomes of the process. As mentioned above, demand at a retail store is a variable. It can be different on every day, right? Now the random part of the definition. A random variable is random because there is chance associated with occurrence of each value. Based on past experiments, the manager of the retail store may know that on a Sunday, there is a 50% chance that the demand from his or her store will be greater than 1000 goods. A random variable is denoted with a capital X and a value taken by capital X is denoted with a small x. To give you an example, suppose that the random process we are looking at is the sales of a store. Therefore, the numerical outcome will be the number of goods sold. The random variable capital X here would be the number of goods sold from the store on a given day. And small x would take different values of sales. So on a given day, if 100 goods are sold, then small x is equal to 100. On another day, it could be 125 and so on and so forth. So based on this discussion, what do you think is not a random variable? Either something that is not random or something that does not vary, correct? So it can be something that can take a single value. A tiger will always be carnivorous, right? No second thought about that. Alternatively, if we know that an event is most certain to occur without fail, which means that there is no chance associated with it, that event would be called a certain event and therefore the associated variable is not random. For example, sunrise on a given day in Hyderabad. We know that the sun will always rise here every day without fail. So fine, we have a random variable. We may have data from past about a certain random variable. What can we do about these numbers? Let's take a look. The idea of probability is key to knowledge of statistics. We hope that you understand it very well. Suppose we are discussing opening a new retail store and we want to know what is the probability that we will break even at the new store in the first month after its opening. Some of you may have a sharp sense of running a business and be very confident that knowing the exact specifications of the store, such as the location, the costs associated, the product mix offered, etc., then it would definitely break even in the first month. Hence, those of you will assign probability 1 to this event, a certain event. Some of the slightly more practical ones would say that there is about 0.5 chance of this occurring. Market conditions, competitions, holiday season, etc. Let me tell you that none of these are probabilities in the true sense. These are just the subjective beliefs. The probability of the store breaking even in the first month can only be calculated using data. One may take a look at 200 similar stores that were opened before this one. If we find that 40 of them could break even in the first month, we will say that 0.2 or 20% chance exists that our store will break even in the first month. So probability is essentially the long run average of random event occurring. The probability of any event E is denoted as shown in the slide. An event can be seeing heads on a coin toss, or selling 1,000 units in the first week of opening a new retail store, etc. As we discussed earlier, probability in statistical terms is much different from a subjective belief. So vague statements such as, yes, most probably I will pass this exam, is not a statement of probability. Then what is probability? Probability is most commonly also understood as the relative frequency of the occurrence of a particular event. By relative frequency we mean the number of times the outcome of our interest is observed as a proportion of the number of all possible outcomes. Therefore, based on 10,000 coin tosses, when we see, let's say, 5,000 of them turn up to be heads, we will say that 5,000 divided by 10,000, that is, half the times we will see a head when we toss a coin. Similarly, as in our earlier example, if I look at 200 new retail stores that were opened, and I see that 40 of them reached a break even in a month, I say that there is 40 by 200 or 0.2 probability or 20% chance of a new retail store breaking even in a month. So in this example, the favorable outcomes were those stores which could break even in a month. In a moment, we will come back to discussing probabilities. First, let us talk a little bit more about random variables. There are two types of random variables, discrete and continuous. A discrete random variable is such that the observations or possible outcomes of this variable can take on a countable number of values. For example, the face value of a randomly chosen card from a well-shuffled deck of cards. This value can only be 1, 2, 3, 4 or so on up to 13. Another example can be the work experience of the PGP class of 2015 rounded to the nearest month. Although too many, these values will also be countable and we can measure each of them. More examples of discrete random variables are the number of smartphones of a particular variety bought from a store, or the number of defective items in a shipment of 1,000. A continuous random variable, on the other hand, can potentially take on one of the infinitely many or countless values in a given interval. For example, the heights of students in a given class, or the profits in the store in a given month. If you notice, the outcomes of neither of these variables can be counted. The profits in rupees can be 1,000 rupees, 1,000.6 rupees, 1,001.2 rupees, 1,001.77 rupees, and so on. More examples of continuous variables that we can find around us are the temperature on a given day, or the conversion rate between dollar and rupee on a given day, etc. On a side note, it is not always necessary that the variable takes only positive values. Take, for example, the profits of a particular store. For a given month, they can be negative. Before we go on, let me note that although it may not seem intuitive to you right now, remember that continuous random variables are much nicer to deal with, and we will understand why as we go along in this course. Now that we have understood what a random variable is, we need a method of describing the uncertainty or the chance associated with a random variable. A probability distribution does exactly that. A probability distribution is a rule that identifies possible outcomes of a random variable and assigns a probability to them. For a discrete random variable, its probability distribution identifies the probability of occurrence of each distinct value. So imagine that in one column, you have a list of all values capital X can take, and in the adjoining column, we note the corresponding probability of occurrence for that given value. Examples of such representation can be a table depicting the results of a coin toss. What is the chance that a toss of a coin will show a head? Or a probability value for an event that a given viewer of a social media advertisement will buy something from my website. Later, if we are interested, we can aggregate the probabilities to find out the chance that the realized value will lie in a certain interval. Whereas for a continuous random variable, the probability distribution by default identifies only the probability of occurrence of a given interval of values. As we learnt, a continuous random variable can take infinitely many values, right? So we can never calculate the probability that a continuous random variable will take a specific value. For example, what is the chance that you will wake up at exactly 6 hours, 32 minutes and 44 seconds in the morning tomorrow? A continuous distribution is a function that gives us the intervals of values of x in one column together with the corresponding probability that small x will lie in the given interval. So instead of tabulating the currency conversion rate being 87.8, 87.87, 87.93, 87.92 and so on, we define the probability that the conversion rate from dollar to rupee on any day will lie between 88 and 89. Here, the conversion rate can take values with as many decimals as we calculate, and therefore there can be infinite values. But suppose we are looking at sales units. Now we can list down the units sold in an interval of 1000 to 1500. The sales can be 1000, 1001, 1002, 1003, 1004, 1005 and so on. But are we really interested in knowing the probability of selling 1006 units and 1007 units separately? Here, it might be easier to consider this variable to be on a continuous scale and define a continuous distribution instead. Isn't that right? This takes us back to a point I made a little while earlier. It might be easier to deal with continuous distributions. In the other part of the preparatory statistics tutorial, you will learn about the most important continuous distribution called the normal distribution. But for now, in this part, our focus will be on discrete distributions. The last 2 points on this slide are properties of a probability distribution. For every value of capital X, that is small x, there must be a positive probability value associated with it. Also, if we add the positive probabilities associated with each small x value taken by the variable, the total must be 1. So as you can see in the formula, if x can take n values, then probabilities of xi, I going from 1 to n, will sum up to 1. So far we have understood what a random variable is, we know the meaning of a probability distribution, and we also learned some key properties of probability distributions. Why don't we take an example and see how to apply these ideas? This example and the one that follows will also tell us how these ideas can help us answer some important questions in a management situation. Suppose you are randomly asked to pick a card from the card deck. What is the probability that this card will be bigger than 10? Let us define x to be a variable which indicates the value of a randomly chosen card from a well-shuffled deck of cards. We know that there are total 52 cards in a deck and that there are 13 distinct values of card existing in the deck. We also know that there are 4 cards of each of these values present in the deck. Therefore, the relative frequency definition of probability tells us that there is a 4 by 52 chance that a randomly chosen card will take a specific value, any value, 1, 2, 3, 4, 13. Now in our question, we have to find the probability that the randomly chosen card has a value greater than 10, which means the value can be either 11, 12 or 13. So the required probability is 4 by 52 plus 4 by 52 plus another 4 by 52, which totals to 12 by 52. You should realize here that alternatively, we could have directly arrived at this answer by calculating that there are total 12 cards in the deck which satisfy the required condition. If you have understood this example well, why don't you try to solve the remaining questions on the slide? The answers to these exercise questions will be shown to you at the end of the presentation, so don't worry, you will have a chance to tally your own answers. I will pause just for a minute so you can note down the questions. I assure you that it will help you a lot if you solve more and more problems. Alright, let's take a look at another example. Here, capital X is the number of large flat panel TVs sold at a store on a particular day. And from past data, we know that it can take values 0, 1, 2, 3 or 4. The probability associated with each of these values is given in the table. For the purpose of illustration, a graph of the probability distribution is also drawn. This type of graph is known as a bar plot. We will study it further in just a few minutes. For now, observe that the x-axis of the graph denotes the number of TVs sold or the values of variable x, and axis y notes the corresponding probabilities. So given this information, can we find out the probability of a sale? That is, the probability that at least one TV is sold? Certainly, when we say at least one TV must be sold, we are looking at the values of 1, 2, 3 or 4 taken by the x variable. Subsequently, we have to just add the probabilities, which correspond to the small x equal to 1, 2, 3 and 4. This addition comes out to be 0.6. Observe that this is equal to 1 minus the probability that nothing is sold. Now, would you be able to tell me what is the probability of selling at least 3 TVs? The answer to this question as well will be available on the same slide at the end. Now that we know what a random variable is, let us discuss a few methods of summarizing one. We are going to discuss 2 ways of summarizing a random variable. The first one is expected value or the mean of the variable. An expected value of x is the weighted sum of its values, wherein the associated probability is used as the weight. Look at the formula. We are adding all the values of small xi over I, weighing each of them with the probability of capital X, taking that particular value small xi. Now why not just take a simple average of values of capital X? That is because each of these values is not equally likely. The Greek letter mu is used to denote expected value of a random variable. Therefore, based on this formula, can we calculate the expected number of TVs sold in our earlier example? In each bracket, we multiply the values of x, such as 0, 1, 2, with their corresponding probabilities, which are 0.4, 0.25, 0.2 respectively. The expected value turns out to be 1.2. What does it mean? Will we sell 1.2 TVs on any of the days? The answer is of course no. This representative value is simply giving us an idea about the centrality of the variable. But how about the variability? Wasn't that one of the key features of a random variable when we discussed it? Here, variance is a weighted sum of the squared deviations from the mean, where once again, The weights are the corresponding probabilities. This measure is nothing but an indicator of the distance of the most extreme values from the mean or expected value. Variance is denoted as the square of Greek letter sigma shown in the slide. It is often referred to as sigma square. As you must notice, this measure relies on squares of distances. So the units of variance are the squared units of the variable. If the variable is measured in centimeters, its variance will be in square centimeters. To work around the problem of having the variance in squared units, we can even look at the standard deviation or sigma instead of sigma square. Standard deviation is simply the square root of variance. Now we have two measures of understanding a random variable better. Looking at the mean and variance can help us characterize the uncertainty contained in a variable. Suppose we know that the average return on a particular stock is 10 rupees. We must ask how much is the variance. We are certainly interested in knowing how bad it can get, aren't we? The mean and the variance were numerical measures. Why not discuss some pictorial summary measures? For the purpose of illustrating all the pictorial representations, we are going to use this data I have. The dataset consists of GMAT scores of all the students in an MBA class of a business school. Here is a bar chart, same as the one we saw in the TV sets example. Against each observed value of the GMAT score, we are plotting the frequency with which that particular score is observed. It is very easy to draw this using any standard software such as Excel or JMP. JMP is the software which you will be using during your course on statistical analysis. Also note that we can easily replace the count on the y-axis with the probability, which is nothing but the relative frequency. But what if our random variable took many more values which are closer than these GMAT score values? The bar chart can then become very cluttered. In that case, we can use one of the two representations that we are now going to discuss. A box plot, which is selected in this red box, and a histogram in this larger box. These are the two pictorial representations we will discuss. This is a box and whisker plot. It captures the spread of the data with respect to 4 quartiles. So the box in the middle contains 50% of the observations. The lower and the upper quartile are those observations beyond which 25% of the observations lie. The range between these two observations is called the interquartile range or IQR. Now, without getting into the calculation which indicates 1.5 IQR, you should note that the outliers are those observations which are very far away from the most typical observations and deserve an investigation. A box plot indicates such observations to us, the ones that are circled in red here. We have to see if something is odd about these values. Given this, we can understand why a box plot is an important tool. We should note that the JMP software will generate a box plot like the one we saw in the earlier slide. The labeling here is done for the purpose of explanation. Now the question is, what is missing here? What if I want to know the fraction of students who get a GMAT score between 680 and 700? A box plot cannot give me this information. This is where our next tool comes to use. A histogram represents a frequency distribution. This is giving us different information than a box plot. We can see that there are more students scoring in the range of 650 to 700 as compared to all other intervals. We can also see that there are more students scoring in the range of 600 to 650 than 700 to 750. Histogram is very similar to the bar chart that we saw earlier. The difference is the histogram deals with intervals rather than point values. Instead of considering each distinct value, it groups them together and gives the frequency or the probability for that group of values. We can see that approximately 200 students score between 600 and 650. And this representation goes back to our discussion about discrete and continuous variable, where we said that even for a discrete variable which takes many values, we can use this method of pooling and turn it into a seemingly continuous random variable. Here is how the probability distribution for such a variable would look like. Now we do not have counts on the y-axis. Instead, we have probabilities. So in keeping with our definition of probabilities, we have turned a histogram with counts into a probability distribution with relative counts. The probability is nothing but the relevant count divided by the total number of observations. So then, as in the similar previous figure, we can say that approximately 30% of the students had score between 600 and 650. If we were to choose a student at random, there is a 30% chance that he or she will have a score in this range of 600 to 650. This is useful because in many cases, we are interested in intervals rather than specific numbers. Although GMAT scores are discrete, the possible values are so large that it can be treated as continuous and it will be very useful for us. Before we end our discussion, let us understand a few more ideas that can play an important part in statistical analysis. Skewness and kurtosis basically make further comments about the shape and spread of any data. You must note that these two concepts are often discussed with respect to normal distribution, the one we will understand in detail in the other part of the tutorial. For now, we will just get acquainted to the ideas. Skewness is a measure of symmetry in the data. So as you can see in the graphs below, the one on extreme left named normal curve is said to have a skewness of 0, indicating that it is perfectly symmetric about a mean value. The other two graphs show positively and negatively skewed distributions based on the shape of the graph. But how do we assign a numerical value to this skewness? How do we know that a particular distribution is more negatively skewed than the other? The formula to calculate skewness in a data is given on the slide. Skewness is nothing but the summation of xi minus mu to the power 3 divided by n into third power of sigma. On the other side is kurtosis, which is a measure of peakedness of a data set. Now this seems to be a definitively graphical analysis, right? Not exactly. Kurtosis value can be calculated using the formula given here. It is the summation of xi minus mu to the power 4 divided by n into sigma raised to 4. Here once again, normal distribution is the standard against which any other distribution is judged. The mesokurtic or the maroon curve here refers to the normal distribution and has a kurtosis value of 3. A distribution with value lesser than 3 and a flatter curve has a platykurtic curve, flat like a platypus, the blue one in our graph. Whereas a distribution with kurtosis value greater than 3 is said to have a leptokurtic distribution, which is taller than the normal distribution as shown by the green graph here, as if it was leaping. Lastly, we will look at the linear combinations of two independent random variables. Independent random variables are those wherein the values of one variable do not depend on the values taken or not taken by the other variable. The simplest example of such variables is rolling of two dice. Suppose I roll two dice together and one of them shows 5 on its face. The value on the face of the other die does not depend on this 5, correct? Therefore, we say that these two are independent random variables. So suppose here we have x1 and x2, which are two independent random variables with means mu1 and mu2 and variances sigma 1 square and sigma 2 square respectively. If y is a linear combination of x1 and x2 as shown in the slide, properties of such a variable tell us that the expected value of y is simply the same linear combination of their respective means. And y's variance is a square into sigma 1 square plus b square into sigma 2 square. This is for the mean and variance of such a linear combination. What about the distribution of y? If we know the probability distribution of x1 and x2, can we characterize the distribution of y? The answer is no. It will be actually interesting and useful to know what is the distribution of this combination. For example, if the sales from two products have a certain distribution and we know it, one would like to know what is the probability that I will make a loss if I sell a certain combination of these two products. So then I want to know what is the probability of my new profit being less than 0. But of course, I need to know the distribution of the net profit. In general, this is a very hard problem. Things are simple if variables have a normal distribution but not otherwise. Why not take a look at an example of a case where it is not easy to characterize the distribution? In this example, we are looking at two dice being rolled simultaneously. Our random variable is defined as the value appearing in the face of a single die. Therefore, this random variable can take values 1, 2, 3, 4, 5 or 6, each with equal probability 1 by 6. Both x1 and x2 are defined this way, so their probability distributions are identical and you can see them in these bar plots. A mean of such a variable is 3.5 and the variance is 2.92. You can easily verify this using the formulae we have learnt earlier. Okay, now we want to take a linear combination. Suppose we define a new variable y, which is the sum of x1 and x2. Therefore, y takes all possible values that can be observed by adding the outcome on die 1 and die 2. Each of you will intuitively understand when I say that the minimum total observed is 2, and this case occurs when 1 appears on both dice. On the other extreme, the maximum possible total is 12 and is observed when both dice turn a 6 on the upturned face. So what would be the mean and variance of y? It's easy to calculate these numbers using the formulae. The expectation of y is a simple addition of expectations of x1 and x2, which turns out to be 7. And the same holds for variance here, because a and b in this linear combination are 1. The variance of y is 5.83. Now how about the distribution of y? Here is a graph in which I have plotted all possible values of y on the x-axis and their corresponding probabilities are on the y-axis. So this is the probability distribution of y. See how different the shape of this plot is as compared to the shape of the bar plots of x1 and x2? How do we characterize the distribution of this variable? We cannot. In some special cases, for example, if x1 and x2 both of them follow a normal distribution, we will be able to characterize the distribution of the linear combination. But in general, we cannot characterize the distribution of a linear combination of two independent random variables. Alright, before stopping, let's quickly go through what we learned in this tutorial. First of all, a random variable describes the probabilities for an uncertain numerical outcome of a random process. For example, marks in an exam or sales for a given period. A probability distribution is a rule that identifies possible outcomes of a random variable and assigns probability to each of them. We then learnt that an expected value or the mean is a numerical summary measure for any random variable and is defined as the weighted sum of its values. Another measure we learnt was variance, and it is defined as the weighted sum of squared deviations from the mean. We learnt about some additional numerical summary measures for a random variable, which are skewness and kurtosis. They help us understand the shape and spread of the data better. We saw how a probability distribution can be pictorially represented by a histogram, boxplot, or a probability density function. Lastly, we studied that the mean and variance of a linear combination of two independent random variables can be calculated, but its distribution cannot always be characterized. Please note that it is not impossible to characterize the distribution of a linear combination of two independent random variables. It is just very difficult. Here are the answers to the exercise questions which were posed to you earlier. Suppose you randomly pick a card from the deck of cards. Probability that the card will be equal to or bigger than 10 is equal to 16 by 52. The card will be smaller than 3 has a probability of 8 by 52. And the probability that the value of the card will be greater than 4 and less than 8 is 12 by 52. For the example on sales of large flat panel TVs, we can calculate that the probability of selling at least 3 TVs from the store on a given day is equal to 0.15. Well, that is all for now. Thank you so much. I hope that the concepts explained in this tutorial are clear to you. Please make sure that you browse through the other pre-course study material in case of any doubts, because these ideas are the building blocks of the coursework you will undertake after coming here. Also, please make sure that you go through the tutorial on normal distribution thoroughly. All the best!